Hello, my name is Abhimanyu, and this is my talk slash presentation on security and mechanism design in DEAI. The main purpose of this talk slash presentation is to propose some open problems and talk a bit about kind of like have like a survey of knowledge kind of a presentation. So let's get started. Uh, we will take a very linear approach to understanding decentralized AI. We'll first start with the definition of DEAI, which has been taken from which I think best represents what DEI actually is, and it's been taken from a paper by Wang et al., which is the Survey of Knowledge of Decentralized AI, which is a really good paper. Then we're going to talk about the background of that's needed to actually understand all of this, right? Whatever we're going to be talking about in general. Then we are going to look into the DAI framework, the framework that every protocol basically uses, follows. At the end of the day, barring some necessary changes in nitty-gritties of it. Similarly, we're going to go into the mechanism of DAI protocols. While I'll be talking about sections 3 and 4, I'll also be outlining some potential problem statements that I think are important. And finally, the last two things that we're going to be talking about are two different attacks that I think could happen, um, and stuff that we could, take care of. These are like my proposals for trying to solve these attacks, if that makes sense. So let's get started. So we'll first start with the definition of DEAI. DEAI is decentralized AI, if I didn't make that clear enough. For us right now, the definition, as I understand it, is that it combines the strengths of both blockchain and AI technologies to enhance the transparency, security, decentralization, and trustworthiness of AI systems. It's basically a combination of AI and blockchain, right? AI being the computational layer, blockchain being the accountability layer or the security layer, right? Uh, so the background that we're going to be needing to understand how all of this works is right here. This is the AI portion. Now, AI being the buzzword here, mostly what we're going to be caring about is this distributed machine learning. More of, we can read more about it in the Breakin et al. Paper, which came out in 2020, which was like an SOK about distributed machine learning as well, where, it's what it basically does is that it solves the heavy computational burden by distributing computational tasks across multiple units, right? Multiple GPUs, so on and so forth. And it does it using two different ways. One being, let me see if I can annotate it. One being data parallelism right here, where the exact data is replicated across different decentralized nodes, and they sit down and they parallelly create models on different subsets of data. And there's the model parallelism, where instead of using the entire data, they compute different parts of the model itself, right? Now, this method is fine. It basically tells you about parallelism in the way you know it right now, right? But what it does is there are some privacy problems, even some computational problems as well when fault tolerance, so on and so forth. So in order to solve that, I mean, not fault tolerance, but privacy was basically the main issue here. In order to solve that problem, there was federated learning, which can be, we can understand more about it from the Zhang et al. Paper in 2021. All of the papers I'm mentioning here are the references. So federated learning basically solves the privacy problem of distributed machine learning, where there is no sharing of data, but instead they share parameters, right? Where different computational units are creating models on their own, and what they do is they just share parameters with one another, which updates after each epoch of training, right? And the third kind here, which I feel is theoretical, there should be like a reference here, is about reasoning agents, which I think we're not too far from, but what do I know? It's basically AI. it's basically agents who can mimic as well as who operate exactly like how a human being does. Like they have a conscience. They can understand pretty much everything that's going on in the world. But again, theoretical concept, we can still consider them as part of something that can happen in the future. I don't think it's very far, but anyways. Let me see. Okay. So, the second part of the background, blockchains, which I don't think I'll have to tell many people here about, which I don't think I'll have to tell you about, is that, um, you know, we start with basically a blockchain here, which is, a distributed ledger technology, which records transactions across a network of operators slash validators, depending on where you are. And the transactions are grouped together in a block, and they are basically linked together in a chain through cryptographic hash functions. And then there's a stamp of approval, in a sense, from a distributed group of nodes through a consensus protocol. And then it just, block is created, block is set up, and then there's another chain, right? Blockchains. Similarly, smart contracts, these are basically pieces of code, I would presume. They're self-executing programs which enforce and execute the terms of an agreement where there are some predefined conditions. Basically, all the stuff, solidity and whatnot, which you use to create contracts on top of the Ethereum blockchain in order to interact with it, right? And so on and so forth. There's a lot of implementations of it in decentralized finance, so on and so forth. Then we have cryptography plus cryptoeconomics, which is basically mechanism design of blockchains and understanding the economics of security in blockchains, so on and so forth. A lot of this work can be found in Monrad et al. In 2019. But getting into the main deal here, yeah, this is basically an overview of the different learning methodologies, right? ML paradigms, where this is where there's like no sharing of parameters or data at all. Everyone's just computing their own stuff, right? And similarly, there's the centralized learning where all the different clients are sending their data to a centralized cloud server, and you can just fetch data from there, just mess with it, right? Similarly, there's distributed learning, which is data parallelism, as we said. The data is completely given to all the different computational units right here, and see data 1 to 5 is being trained by GPU 1, data 6 to 10 is by GPU 2, data 11 to 15 is by GPU 3, so on and so forth. And then the parameters are given back to the parameter server right here. And there's the centralized federated learning, where the different clients are computing their own data points, and they are contributing it to a single server, similar to the cloud architecture that we see right here. Then there's the decentralized federated learning, where there's basically a peer-to-peer network going on, which is the ring all reduce right here. The network topology here is a ring all reduce, where there's a peer-to-peer network amongst them, and they're sharing it with each other, right? Then there's decentralized learning, where, as you understand it, there are training nodes and there are basically clients and voters, right? And then basically, again, it's similar to decentralized federated learning in the P2P network sense. But at the same time, what's really happening is that the training is done by the nodes here, while the consolidation of those trained parameters are done by the voters right here. So going towards decentralized AI framework right here, the framework here is basically composed of 4 different tasks, or tasks as in 4 different functions, right? The whole process starts with a node proposing a task for the entire network to solve. For example, if I'm someone who wants the network to make an ML model based on my, I don't know, based on some insurance data or some any data whatsoever, right? I would give them a task to predict what my insurance claim amount payout is going to be given I do this, right? So on and so forth. That's the task proposing area. Then there's the pre-training where we uh, pre-align the data in a sense, where we take care of. Yep, there's the pre-training. What we do is that's where the data curation happens. The data is made so that it could be used by the training nodes in the next section. But it's basically where there's data preparation as well as compute preparation. We make the data available to use, and at the same time, computational resources available for use as well. Then we have the on training, where once the data is prepared, the computational resources are prepared. It basically focuses on how information and updates are managed safely. What happens is in this step in in on training, not pre-training right here. In on training, there's model preparation as model training as well as model validation, where model training, the participating nodes, they collaboratively update the model parameters by processing on data sets and maintaining synchronization amongst them. Then there's the model validation, where the trained models are evaluated based on some benchmarks, right? Then there's the post training, where after the model verification has been done, all the modeling, this is the part where they go from model deployment to they go from model development to model deployment in a sense, where inferences are drawn in this exact setup, right? And so during model inferences, what they basically do is they use the trained model to generate predictions, right? So this is at the end of the entire process, where, okay, if I wanted to know how much payout I might get from like an insurance, based on the insurance claim amount that I've submitted, this is the portion that tells me, gives me the answer to that question, along with some loss metrics as well, loss functions, which will basically tell me how wrong they can be at the same time, right? So all of this can be sorted out using some mechanisms where there's decentralized incentive mechanisms, cryptographic mechanisms, so on and so forth. This is basically a way to secure this entire system. But yeah, so yeah, this here tells us a lot more about what I've been talking about right here. There's decentralized algorithms right here. There's the task creator who basically wants to give us some tasks about either it's a data sharing based task or model sharing based, so on and so forth. There's also code verification here, where they download the code from the verification committee who put it on the blockchain right here, right? Who staked it on the blockchain, and they're rewarded by the code verification. And then the code goes to the uh, after they've achieved consensus, the code goes to the decentralized storage. I think it's an off-chain storage system right there. Then there's the pre-training, where there's a decentralized data preparation. What basically happens here is that data is being uploaded to a distributed set of data validators who will basically this is an entire part that we have to talk about right after this. Um, this we'll talk about this. We'll talk about all of this once I'm done. Once we'll go down, actually, I think it would be better. But yeah, so pre-training, as I said, after task proposing, what comes is pre-training, which is basically a combination of data sharing and compute sharing. So for data sharing, there are, as I said, incentive mechanisms for data contribution. There's basically tokenization of data. And now what I mean from that, what I mean by that is that there's, you make tokens out of data, right? Where say there are some protocols like Ocean Protocol and Mana. What they do is they have basically make a marketplace where data assets are tokenized and they can be bought and sold, right? Bartered, so on and so forth. Data consumers can purchase these tokens to access or use the data, and they can also use staking and curation to promote high quality, data contributions, where it's like solving the nothing at stake problem right there, right? They stake data like it's assets in a sense. And then there's the proof of data contributions and scoring. So given the staking protocol that we've talked about in data tokenization, there is something called proof of data contribution, which I think was done by Vanna in a sense. Uh, they are responsible for evaluating data quality, and they apply a predefined function to quantify each data point's contribution and assign scores based on its calculated influence. right? Which basically means basically using influence functions and whatnot, where okay, if there's a data set that's already there, they look at how addition of a data point improves or depreciates the quality of the data set that's already been there, right? Then there's the stake and reputation-based rewards, which makes sense. The better the quality of data you submit, the better your reputation is, and the better rewards you might get, so on and so forth, which is similar to the proof of data contributions. But there we want to keep it as like a decentralized addition, a decentralized contribution to one whole data set, rather than everyone contributing different data sets altogether, right? If that makes sense. For data privacy, there's the option of using ZKPs plus encryption, but the problem with that is extreme amount of computational burden. Even before the process starts, you're gonna have to there's gonna be a lot of loss in time in order to just even have one whole epoch worth of training data available, which is not worth it. Similarly, at the same time, there's also talks of using TEEs in a sense, which can again be used. I haven't looked into it too deep, but I'm pretty sure I should. Then there's like side and sub chains, which basically are, just like sub data chains, if that makes sense. Something that I think some protocols have done. I need to look deeper into it, but I've kept it here just in case anyone, like, if you have any ideas about it, um, in case like this might be something that could be used in the future. And then there's the vector databases for LLMs, which is encryption support, whatnot. I feel that this is basically how you would contribute data to LLMs right here, basically using vector databases, what Pinecone and others have done. All it needs for data privacy right now is encryption support. But then again, the thing is, if you encrypt the data at the source, are we going to be using stuff like homomorphic encryption and stuff like that in order to use the data, make the data available for training? If so, how can the LLM be able to identify between the original source data and what if it interprets it as something else, like lost in translation, stuff like that? There's a potential problem right here where I have mentioned, which says, is there a decentralized way to avoid data sharing in such a way where nodes in a PvP network don't end up independently sharing data that can be used to conduct linkage/differencing attacks? In other words, can we create optimal bounds to ensure k-anonymity in different data sharing models without the interference of a single authority? What this basically means is, say, for example, it's data which is very um, insecure, right? Not insecure, it's private, it's very sensitive. For example, health data, right? My, as I said, my bank data. Can I share the data in such a way where nodes in a PvP network, in a decentralized training network, they don't independently uh, they don't share the data that can be used? Because, okay, let me rephrase this. Say, for example, I have a node who wants to share data, right? Which is very personal to me, but at the same time, my markers of my identity are left out, which is fine. But what if someone else shares a similar data set, which has nothing to do with my bank data, which is different, but at the same time, there's one factor that can be linked between those two data sets, right? If that happens, my privacy is completely gone. But on the other hand, it is really good for the model because the data, the influence functions right here, the model influence function, it will see that the addition of the new data point is actually really good for the model to train because it gives the model a lot more information to work with. So even though the ML model is completely fine, the ML model is happy with the data that it receives, it won't be able to, it actually destroys my privacy completely. So can we make optimal bounds based on it? Can we think of more cryptographic methods of figuring out, or maybe some incentive-based methods, some checks, right? Some decentralized checks, maybe. Uh, Maybe we use eigenlayer in this here. A lot of different ideas right there about this. Similarly, there's compute sharing, where basically there's containerized workloads on idle compute nodes. There's different ways in which we can do compute sharing, some of which are there are containerized workloads on idle compute nodes all over the world. You can just there are idle compute nodes there, just go use them, right? Similarly, there could be a decentralized marketplace of GPUs as well. Similarly, like how you did it for data, make a marketplace for GPUs instead. There can be an aggregation of compute resources from a global pool of contributors, like how they do it in mining, right? Which is shared mining, from what I understand. Mining pools, right? Everyone computes their respective compute sources and they delegate their stake, right? And people from the outside can delegate the stake to them for computing for them. And then there's multi-party computation, good old-fashioned multi-party computation. So a potential problem statement here would be an incentive model for compute sharing, right? A very nice, succinct compute GPU sharing marketplace with additional incentives, because um, this isn't as simple as buying data. This is a bit more convoluted because now we're doing GPUs instead, which do suffer from wear and tear. A lot of different factors come in that people in general don't really think about, right? Then this is on training. As I said, on training had two different uh, parts, which was model training and model validation. So in model training, the participating nodes collaboratively update model parameters by processing local or public data sets and maintaining synchronization, as I said, which makes sense. We've talked about it before. The model validation is when the trained models are evaluated on a shared validation data set or through cross-validation to ensure their accuracy, like how you do it in standard regression models, right? Uh, So yeah, what's more interesting here is a potential problem statement where collaborating nodes are training parameters. We need to have a consensus plus incentive mechanism that discourages model stealing and attacks. So what if a training period goes by in the on-training segment, but instead of training their own parameters, they use a model from somewhere else, right? One or two people do this, that's fine. But what if an entire network ends up doing this, which is basically comes under model stealing, right? Where they might steal their own model or other people's models. But at the end of the day, they're only going to be just regurgitating the same exact parameters again and again, which makes no sense, right? Which they shouldn't be doing. But if they do it, even the consensus can't stop them that easily because that's the source of truth, right? Can we make generalized bounds using differential privacy methods that it would be optimal trade-off between security and scalability, right? If that makes sense. Where what if there is a way that there is uh, how can we scale the whole idea of on training? How can we scale the total number of trainers while at the same time keeping the security risks to a minimum, right? So it's basically a security trade-off right there, where it's either you make a secure protocol or you make a scalable protocol, right? Which is basically, as I've written it right here, um, the CAP theorem in distributed systems. It reminds me at least of that. Now I'm going to mention something about a scaled bribery attack, which is basically similar to one of the, I think this is pretty much like a whole problem statement right there. Um, what I wanted to mention here was that given a data sharing plus training model that we've talked about till now, how can we prevent training nodes from bribing data sharing nodes, right? So there's the I am a task. I gave this network a task of figuring out my claim payouts based on um, based on my credit history, based on my insurance claim history before. And or you know what, scratch that. Let's think about a different task where figure out whether I'm going to have cancer or not, right? That's basically a training task where I want everyone to have all my health information from the past 23 years of my life. That's what I give to, I divide it amongst the data sharing peeps who basically contributed without any personal links to me to the training protocol, right? To the training nodes, who basically use that data to train a model, right? But at the same time, they don't know it's me. But on the other hand, if they find another data set that has some sort of link with me, it causes a linkage attack, and the my health data, and maybe they have access to my bank data, and maybe they have access to my, my like some other random data that caused the linkage in the first place, right? Which may be related to something which is lateral to health as well as my financial data. But it's extremely obvious that all of those three data sets are about me, right? So as I said, how do we prevent training nodes from bribing the data sharing nodes, right? To share data sets that will be overall catastrophic to the user whose data has been used, right? But ultimately beneficial for the system, because as I said, once they figure out that because they are getting more and more data about me, right? The model. And so the model influence function that we're going to be using, right? The data influence function, right, that we're going to be using is actually going to be the metric is actually going to be better, because the more information that the data point adds to the model, the better the influence is going to be, right? So is the execution power for, in order to solve this problem, is the execution power needed asymptotically close to a kamikaze attack, right? Where is it so that in order to actually implement this attack, is it so, intuitively speaking, is it equivalent to conducting an actual kamikaze attack on the system where I take all the money and I'm going to essentially have to destroy the consensus, destroy the like have enough economic power to destroy the consensus and have a majority lead in the system itself, right? Is it asymptotically close to that, or do we have any better bounds, right? Similarly, there's also an AI agent attack here. This is now coming back to the reasoning agents that we talked about, who act like human beings, talk like human beings, right? So assuming AI agents can reason and learn continuously to make adequate decisions to maximize net utility, given computational constraints, it is obvious that like human beings, AI agents will sometimes, if not every time, will choose to do less to earn more, right? Like reward hacking and stuff like that, which may include attacking other agents, right? Spoofing other agents to get them out of competition in betting markets. With that, what I mean is, for example, there are two AI agents, or kind of like two human beings, who are betting on a coin toss, right? Assuming one of the two agents is extremely rich, they are going to bet a huge amount of money on, say, heads, right? And the other person, the other AI agent, won't have any choice but to go all in on any of the options it chooses, right? So if the AI agent, the rich AI agent loses, no harm, no foul. But if the poorer AI agent loses, he's out of the market. The AI agent is out of the market completely, right? Which is good for which is overall good for the winning AI agent in the first place, the richer AI agent in the first place. So there could also be like low-hanging rewards like transaction ordering, auctions, all the stuff that we have done, that we've looked into in MEV literature right now. So how can we align these agents in a decentralized system? And if it is even something that we should be working on, right? Because I know that it's sufficiently easier to try and align these agents in this decentralized system, because they do operate on complete rationality. But is it something that we even should be doing, right? Because these AI agents hopefully are going to be, assuming these AI agents can't reason up to a point that they are human beings, they are going to be used by human beings. So either ways, there is going to be someone of human capability interacting with these systems in the first place. And they will be the ones who will be um, trying to game the system no matter what happens, right? So this falls under AI MEV. There's a really nice ROP by Robust Incentive Group, which is, I've mentioned the link right there. Feel free to look into it. And yeah, there are a lot more problems to solve. I didn't even cover some others right here. But this is all I have for now. Thank you so much for your time.